Alright, today we are going to discuss Chapter 4, Digital Transmission. So, last class we talked about the physical layer, and today we are going to carry on. Also, we are staying in the physical layer, but we want to see how the data is transmitted. And we are going to look at the digital data, which is the data that we have at our computers, the zeros and ones. We will see how the physical layer is encoding these data and sending these data on the link. So that is the goal of Chapter 4. So the outline of today's talk, we will explore digital to digital conversion, and we will talk about different transmission modes. So, in today's class, we are going to see how we can represent digital data as a digital signal. So, we will talk about different encoding techniques, how we can convert these digital data on the computers that we have zeros and ones into a digital signal that can propagate on the link and go to where it's supposed to go. So, in this topic, we will talk about three digital to digital conversion. One is called line coding, the other one is called block coding, and the third one is called scrambling. So in the line coding, every technique we will talk about, we will use the line coding. For the block coding and scrambling, these we will be using them in special cases, which we will learn later on in this chapter at the end. So we will start with the line coding. What we mean by line coding? Line coding is the process of converting digital data to digital signals. So very easy, we have digital data, zeros and ones, and we want to convert them to a digital signal. We call that line coding. This graph represents the line coding and decoding. So here we have a digital data. The digital data here is, of course, produced from computers, can be computers, laptops, or any other device. So we have zeros and ones. At the sender side, we will have an encoder. The job of the encoder is a device, and the job of the encoder is to encode the digital data into digital signal. Now, this is what we are going to focus on this chapter, how we are going to do the encoding, and we will talk about different techniques on doing that. So once the digital data propagates through the link and reach to the other side, at the receiver side, we will have a decoder. The decoder job is to transfer the digital signal into digital data that the computer can understand and can work on it. So that is basically what we mean by line coding and decoding. In order to follow up with this chapter, we want to see what we mean by signal elements and data elements. What does signal element mean? What does signal data elements mean? So as you can see in this figure, what we have 3 bits, 1, 0, 1. And the way we are representing these 3 bits using negative voltage and positive voltage, as you can see here. So each one of these bits, this is what we call it. From here to here, we call it bit interval, right? That's the duration for 1 bit on the link. So this is called the bit interval. So here, one data element, which is 0 or 1 in this case, is represented by only one signal element. So this is the signal element, and this is the data element. So this one, how many signal we need to represent this one? Only one, right? So this is the only signal. We need only negative signal, one negative signal in order to represent one. So R, in this case, R equal 1. What is R? R is the number of data elements carried by each signal element. So number of data elements carried by each signal element is 1. Okay, 1 over 1 is 1. If we take a look at this here, we have two signal elements here, and we have only one data element. So the R will be 1, which is the data element, over 2, which is the signal element. So the ratio here, R, it represents how many data is carried by each signal element. In the third here, we have two data elements, and how many signal elements? Only one. So the R equal 2, which is 2 over 1. In the fourth graph here, we are sending 1101. So each time we are sending 4 bits. Okay. How many signal elements we need to send 4 bits in this graph here? We have 3 signal elements. So R equal 4, which is the number of bits, over 3, which is the signal element. Why we need to understand that? It's very important to understand the ratio of the data element and the signal element, because we have something called data rate and we have something called signal rate. What is the difference between data rate and signal rate? Data rate is how many bits we can send per second, right? That's the data rate. So by adding or by encoding more bits per signal element, we can achieve higher data rate. For example, here we have only one data element per signal element, but here we have 2 data elements per signal element. That means that the data rate here is going to be higher than the data rate here. So our goal is to increase the data rate. Also, our goal is to decrease the signal rate. Why? Because when we have more signal rate, that means what? We need more bandwidth. And more bandwidth means more cost. So our goal when we design the encoding is to keep the signal rate low. So for example here, the signal, which one of these has higher signal rate? This here or this here? This one, right? Why? Because we have 2 signal elements here per bit interval. While here, this one has the highest signal rate. We have 3 signal elements per bit interval. So this one is the highest data rate. So just keep in your mind what we mean by signal element and data element, because we will use that in the next slides. One other thing we need to also focus on while we go through this chapter, synchronization. Sending data or digital data through a link, it's guard, but what we call synchronization. Synchronization is the timer of the sender and the timer of the receiver need to be synchronized in order to receive the data accurately. So in this figure here, what we have, we are sending 10110001. So this is the data we are sending at the sender side. What we are getting here at the receiver side, we are getting more bits. We are getting 110, 1111, 000011. So how many bits we are sending? 1, 2, 3, 4, 5, 6, 7, 8. We are sending 8 bits. We are receiving 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Sending 8 bits. We are receiving in the receiver side 12 bits. Why is that?
The time is not same.
Exactly. The time is not synchronized between the sender and the receiver. As you can see here, the time for each bit interval here is that much, but here is much more smaller. That means the clock at the receiver side is it what faster than the clock at the sender side. And if they are not synchronized, that's what we get. We send something, we get something else. So it is very important to synchronize the time between the sender and the receiver so we receive the same bits that we are sending. And why I'm talking about synchronization here, because we will see how the encoding, different encoding techniques will help us maintain the synchronization between the sender and the receiver. And we know why this is important now. In this example, in a digital transmission, the receiver clock is 1.1% faster than the sender clock. How many extra bits per second does the receiver receive if the data rate is 1 kilobit per second? If the receiver clock is, or the data rate is 1 kilobit per second, and the receiver clock is 1% faster, we will receive 1 extra bit. So basically, we are sending 1 kilobit per second. That means we are sending 1,000 bits per second. Multiply that by 1%, which is 0.01, right? And that will give you 1. So that is 1 extra bit. So we are sending 1,000 bits, we receive 1,001. What if the data rate is 1 megabit per second? 1 megabit per second is what? Is 10 to the power 6, right? 10 to the power 6 bits per second. Multiply that by 0.1%, 0.1%, and that's equal 10 to the power 3. So we will have 10 to the power 3 extra bit if the data rate is 1 megabit per second. So higher data rate on the link, if we have a unsynchronized link, that means more extra bits that we will receive. So in the line coding schemes, as I said, every time we send digital data as a digital signal, we will do what we call line coding. So there are 5 broad categories for line coding. We want to divide them into unipolar, polar, and bipolar, multi-level, and multi-transition. So in the what is that? So in the unipolar, we will discuss non-return to zero. In the polar technique, we will discuss, in the polar category, we'll discuss a few techniques. We will discuss the non-return to zero and return to zero, and we will discuss also Manchester and differential Manchester encoding. So there are like 4 different techniques in the polar category. In the bipolar category, we will discuss AMI and Zeedu ternary techniques. We'll discuss 2 techniques. For the multi-level, we will discuss the 2P, 1Q, and 8B, 6T techniques. So we will see what are the advantages and disadvantages of these techniques, what are the things that they can provide, what is their shortcoming things. The last one is the multi-transition here. We're not going to discuss it, but I kept it here so you know that we have 5 categories, but we're not going to go to the multi-transition in this chapter. So we'll end by the multi-level category. So unipolar or non-return to zero scheme, it is called unipolar. Why? Because it is only on one side of the time axis, right? Only on one side. So that's why we call it unipolar. So how the unipolar works? Unipolar works as the following. For 1, we will have positive voltage, for example, as you can see here. For 0, we have absence of voltage. So that is how basic is that. So if we have another 1 here, what we will do, we'll just continue. We'll do transition to a positive voltage. If we have another 0 here, we'll go back to non-voltage, absence of voltage. As you can see here, very simple technique. Because it's very simple, it's not used nowadays. It has many disadvantages. One of the big disadvantages here is the DC component, or what we call it the direct current. So you know what is DC component? DC component, when we have a long runs of zeros or ones, that will lead to what? That will lead to another small frequencies. That is because of Fourier analysis. So that is small frequencies called DC or direct current, and that is bad for the transmission of the digital signal. Why? Because that becomes as a noise to the digital signal. So we try always, when we send digital signals, to stay away from any techniques that generate direct DC. So why these techniques generate DC? Because these techniques, if we have one, long run of one or long run of zeros, we are not changing the polarity of the signal, right? And that's what caused the DC to appear on our transmission link. So that is one of the disadvantages. Other disadvantages of this technique is the synchronization. There is no way to synchronize between the sender and the receiver. There is no, like as we will see later on, there is no mid-bit transition that led to the synchronization. That's another disadvantage here. So there's, because of these two disadvantages, this is not used anymore. So this is the polar schemes, the second category. Polar schemes, we have two techniques. One called non-return to zero level, and the other one is called non-return to zero inverted. So non-return to zero level, how it works? For zeros, we have, as you can see, we have a positive voltage. For one, we have a negative voltage. So we are not transmitting. There is no mid-bit transition in this technique. What is the difference between this technique and the one before? This is we don't have an absence of signal. We don't return to a zero level, right? And this is a bipolar. Why? Because we have up above the time axis and below the time axis we use positive and negative voltage here. But looking at this, we can identify same problems that we identified in the previous one, which is when we have a long run of zeros or ones, we have also a problem with the synchronization, right? And also we have a DC component here. For the non-return to zero inverted, we will invert every time we have a digital bit of 1. So as you can see here, because we have 1 here, we did a transition here. Again, we have 1 here, we did a transition at the beginning here. We have 1 again here, we did a transition. 1 again, we did a transition here. Because we have 0, we have no transition. So basically, if we have 0, we do not transition. If we have 1, we do transition. So the non-return 0 inverted is not that bad as the non-return 0 level. So if we have a long run of 1, what we are doing, we are transiting from positive to negative, right? So the synchronization, if we have a long run of 1, is not that bad. We can synchronize because we have a transition. But if we have a long run of zeros, that is a big issue with the non-return to 0 inverted. We will lose synchronization because of that. Also, the DC component is not that bad as the non-return to 0 level because we are changing polarity for bit 1, right? From positive to negative, but only when you have a long run of 0, DC components will appear. We will see how we will come up, how we will resolve the issues with the non-return to 0 inverted when we talk about scrambling. So we will see how that is resolved, and we'll see how we will resolve the non-return to 0 level non-return to 0 level problems when we talk about Manchester differential Manchester. So the other techniques used in the polar scheme is called return to 0. So return to 0 here, it has a transition in the middle of the bit interval. As you can see here, for 1, for 0, we have always a transition at the middle of the bit interval, as you can see here. Always we have a transition. Point them out here. And basically what we will do for 0, we'll transit from negative to 0. For 1, we'll go from positive to 0. For 0, again, we go from negative to 0. For 0, negative to 0, and so on. For 1, from positive to 0. So that's basically what is return to 0. Because we have a transition at the middle of the interval bit, we are doing synchronization. So the middle transition for each interval bit, it is used for synchronization. So synchronization problem is not existing here in this technique. How about DC? Do we have a DC problem here? This looks like I'm talking to myself here. Okay, so we have two issues when we transmit digital data, okay? We talk about the synchronization issue and we talk about the DC. So we said that the synchronization issue happens when we don't have when we don't have a transition at the middle of the bit interval. But in this case for RZ, we do have a transition in the middle of each bit interval. So that transition will let the clock at the receiver side adjust its time, so we'll keep the synchronization between sender and the receiver. So every time the clock at the receiver side sees this transition at the middle of the bit interval, will make sure that its time is according to that transition. How about the DC current here? We said when we change the polarity from 0 to 1, 1 to 0, 0 to 1, 1 to 0, from positive to negative, we cancel the DC current, right? So as you can see, for 0 here, we are going from negative to 0. For 1, we are going from positive to 0. So these two, they cancel each other. That's why we don't have a DC component here. We don't have a DC component because we are changing the polarity. For 0, we are going from negative to 0. For 1, we are going from positive to 0. So they cancel each other. So there is no DC component here. Then this is a great technique, right? Nothing is great in this life. Everything has shortcoming, right? What is the disadvantage in this technique? Can you point it out? Excellent. Extra signal element. We talked about signal element, and we said when we have more signal element, that leads to have what? More
bandwidth.
Excellent. And having more bandwidth means more cost. We always try to keep the bandwidth limit. Having a wide bandwidth for the link is great, but asking the signal to use a lot of that bandwidth, that is bad. So we need to keep the signal using a limited number of the bandwidth that we have. And because we have two signal elements, as you can see per each bit, that means the R ratio, it is 1 over 2, right? One data element over 2 signal element. And we said that is not a good thing to do. So that is the only disadvantage here. So why we don't combine, since we like the middle bit transition here for synchronization, and we like the changing of the polarity of that technique, but we didn't like the 2 signal element. Why we don't combine this with the non-return to 0 level and non-return to 0 inverting and come up with another technique that have both advantages? So this is what we did here in the Manchester and differential Manchester techniques. So Manchester techniques here and differential Manchester, both of them use what? Use a mid-bit transition. And the mid-bit transition for Manchester and differential Manchester is used for what? Synchronization. Excellent. So that is one of the things that we used, which was an advantage in the previous technique. The other thing, in the Manchester, what we did, we transitioned from high to low, and for 1 we transitioned from low voltage to high voltage. So both of this will cancel what? The DC current. Good. But what?
The ratio is still the same?
That's a good question. Is this here the ratio still the same? Yes, the ratio is still the same. But there's one difference between Manchester and the previous one, which is
The signal is in half.
how many signal level we use in the RZ. We use 2 signal elements, but how many signal level we use in RZ? 3. Having more signal level, what will lead to? A complex system. At the receiver side, instead of the receiver side differentiate between only 2 levels, now the receiver side needs to differentiate between 3 different levels. And that was removed in the Manchester. In the Manchester, we have only 2 levels. That's true. We do have 2 signal elements, but we eliminate the number of signal levels in the Manchester. In the differential Manchester, what we have, how the differential Manchester U is working? It's working as the following. If we have 1, we don't do a transition at the beginning of the bit interval. But if we have a 0, what we do? We do a transition at the beginning of the bit interval. So if I give you any code, any data, any bits, you will be able to translate it into Manchester and differential Manchester. What if we have here 0, 0, 1? If we have 0, 0, 1, what we will do for 0, we'll go from high to low. Let's put the interval here. So we'll go from high to low. Then we have 0 again, so we have to go high to low. Then we have 1, so we'll do low to high. And here, what we will do for differential Manchester, if we have a 0, what we will do, we have to do a transition at the beginning of the bit interval. As you can see here, we have 0, we did a transition at the beginning of the bit interval. We have 0 again, we have a transition at the beginning of the bit interval. We have 1, we don't do a transition. We have 1, we don't do a transition. So here we have 0, we have to do a transition. We have 0 again, we have to do a transition at the beginning, and then we go. We have 1, we don't do a transition. So it is not about high to low, low to high in the differential Manchester. Is it about if we have a transition at the beginning of the bit period, or if we don't have a transition at the bit period? That's what determines if it's a 0 or 1. So by looking here, we have a transition, that means we sure have a 0. We don't have a transition, we sure we have 1. Transition, 0. Transition, 0. No transition, 1, and so on. While in the Manchester techniques, we will not do a transition at the beginning of the bit period unless we have to. Or the transition at the beginning of the bit interval doesn't mean if we have 0s or 1s. What is guarding the 0s and 1 if we are doing high voltage to low voltage or low voltage to high voltage. So for example here we are doing high to low, that means 0. We are doing low to high, 1. High to low, 0. High to low, 0. When do we need to do a transition? At the beginning of the bit period in the Manchester. When we have 2 consecutive 1s or 2 consecutives or more of 0, right? Okay, the advantage of Manchester and differential Manchester encoding, as we can see, is synchronization. We are doing synchronization. How we are doing synchronization?
Converting the bit in the middle of the...
Exactly. By having a middle transition for every interval, will help in the synchronization. So that is advantage. Another advantage of using Manchester, differential Manchester, is there is no DC component. That is great. What is the disadvantage of the Manchester, differential Manchester, is, as he mentioned, that we have 2 signal element per bit interval. 2 signal element per bit interval. That is a disadvantage here. So the other techniques, or the other category we want to talk about, is the bipolar schemes. We have 2 techniques here, one called AMI and the other one is called ZB ternary. AMI is alternate mark inversion. Alternate mark inversion. What we mean by mark? In the Latin language, mark is meaning 1. So alternate 1 inversion. So when we have 1, we will do an alternate polarity. That's what it means, AMI. So for 0, we'll just have absence of signal, as you can see here. For 1, we just alternate from positive polarity to a negative polarity. So here we have positive polarity. Then when we have another one, we'll do negative. When we have another one, will do if we have 1 here, for example 0, 0, we will have a positive polarity for 1, then we have an absence of signal for 0, 0. So this is an AMI. Z2 ternary is exactly like AMI, just the opposite. We will do alternate for 0 instead of 1. Alternate polarity for zeros instead of 1. So zeros, as you can see here, will alternate the polarity, positive, negative, positive, negative. For 1 will stay absence of signal. So now maybe you say, okay, why you are doing this? We are back into the same problem. Now we have a synchronization problem, right? When we will have a synchronization problem with AMI, when we have a long run of what? A long run of zeros. Good. For AMI, the synchronization problem will appear when we have a long run of zeros. Why? Because when we have a long run of zeros, we are not changing the transition, right? And that most of the time will make the signal at the receiver doesn't know when the bit interval start, when the bit interval end. We are not doing transition. So that is a big problem with AMI, but there is a big advantage with AMI and Z2 ternary, which is how many signal elements we are using. We are using only one signal element. That is a big advantage. So when we use every one of these techniques that I am explaining, we use them in a different scenario. For example, AMI and Z2 ternary is used for high data rate for long distance communication. So it's used for long distance communication where we don't need to consume a lot of bandwidth, and where we can also fix the synchronization problem, as we will see in the scrambling technique. So long run of zeros will be fixed later on. We'll use this technique, but we will fix the synchronization problem. Same thing with the Z2 ternary. Long run of 1 actually will make a problem with the synchronization, so that will be fixed as well. Also, we have a DC component. No, we don't have a DC component here. Why? Because we are changing the polarity for the positive and the negative. And of course, 0 doesn't have a DC component, as we know. So there's no DC component, only synchronization problem with this technique, which we will see how we will fix it later on. Now, maybe you're asking questions. Okay, you did not show us any technique to send more data. Okay, we have seen a technique where we send only 1 bit per bit interval, right? But we want to see also techniques that can provide a higher data rate. So this is why we have a multi-level category. In the multi-level category, we can send 2 bits, as you can see here, per bit interval, and that will lead to a higher data rate. So 2B1Q represent how many bits we are sending per bit interval. We are sending 2. B is for binary. We are using zeros and ones. 1, it means how many signal elements we have. In this technique, we have only 1. So this is the 1. And the Q is for quaternary, what we have 4, the number of signal level. Here we have 4 signal level, and the Q is for representing that. So it's a very simple technique. For 0, 0, we'll just use -3. For 0, 1, we specify what voltage or what level we will use for each 2 bits, and we just code it as you can see here. Why we use multi-level? If we need higher data rate, then we can use multi-level. This is another multi-level technique. Is used for encoding to provide high data rate. In this multi-level technique, what we have 8 bits. It's called 8B60. 8 for what?
8 bits.
8 bits, exactly. So we are sending 8 bits, as you can see here. And B is binary, zeros and ones. 6 for what? 6 signal elements. 1, 2, 3, 4, 5, 6 here. And T for trinary, which is for the signal levels. Here we have 1, 2, 3. 3 levels, as you can see here. So by having 8 bits, how many different data bits we can encode here? We can encode 2 to the power 2 to the power 8, right? We can have 2 to the power 8 different combination of 8 bits. So that's equal how much? 256. 256 different bits we can send. How many signal element we will have? We have, as we know, we have 6 signal elements. What is the combination of different signal elements we have? What is the number of different signal elements we have? 2 to the power? Oh, sorry, it's a 3 to the power 6, right? Because how many levels we have? 3 levels, and we have signal elements, so 3 to the power 6. 3 to the power 6 is around 700. So we have 256 data. We have around 700 different shapes to represent the 256 data. So that means we have more signals. We keep it, saved somewhere. We will use them for different things. We will use them for control data. We will use them for error detection. We will use them to prevent the DC component. So let's see how we use that actually. So here we are sending 0001001. Okay, so that is the bit we are going to send. By looking at the table, we have a table for each 8 bits. We will know which one of the signal element or which one of the signals we have to use. So by looking at the table, this is the signal element that we are using. If we want to see that, that is negative, 0, negative, 0, positive, positive. What is the polarity of this signal? What is the polarity of this signal? As you can see, negative cancel positive, negative cancel positive. So the polarity of this signal is what? 0. If we look at this, we have 0, 1, 0, 1, 0, 0, 1, 1. And if we look at the table, we will find out this 8 bits will use this shape of the signal. What is the polarity of this signal?
Plus 1.
This is plus 1. Then we have 0, 1, 0, 1, 0, 0, 0, 0. And that, when we look at the table, we find this is the pattern that we will have to use, which is plus, minus, plus 0, which is also plus 1, if we look at the pattern of that. But actually, is this the one that we use to represent the signal? No. This is, where is the mouse? Do you see the mouse? Okay. So this is the plus, minus, minus, plus, 0, plus. This is what we have to use to represent the analog signal. But we did not use that. We used a negative, plus, plus, negative, 0. We inverted that. We inverted the signal that we're supposed to use. Why we did that?
To cancel it?
Exactly. We did that to cancel the polarity, to make this, instead of plus 1, to make it negative 1. And that's what we did exactly. So this can cancel that. So the rule here, by using 8B6T, when we have 2 consecutive 8 bits that are using 2 signals that have both plus voltage, what we will do, we'll invert the second one as we did here. This is an inverted one, such that we can get negative 1 and they can cancel each other. So that's why we are using the inverted to cancel the DC component from the 8B6T technique. We got the idea how we cancel? Good. So now the questions for you is how the receiver will know that this is an inverted and this is not the actual representation of the bit. How the receiver will know that this signal here is the inverted signal and not the original one like this one. So how the receiver know that, so it can re-invert it back and decode the right bits instead of having the wrong bit. Every time, that's how the receiver knows. Every time the receiver receives a signal, its polarity is negative, it will know it is inverted. That's basically the rule here. Every time the receiver will receive a signal, its polarity is negative, it will know that it is originally was positive and it was inverted. How we can achieve that? We can achieve that because we have 700 different signal elements. We can represent only, we can use only 256. So the 256 we are using, all of them has positive polarity. So out of the 700, all of the ones that we are using to represent the different 256 8 bits are having positive polarity. We're keeping the negative polarity away. So whenever we receive anything negative, we know it's not the original 8-bit, so we have to invert it. So it's clear here? Okay, good. So while we are using 8B16, there are many other techniques. As I said, we can use 10B17, which is 10 different bits sending over 7. That depends on the application, depends on the data rate. Higher bits per bit interval mean high data rate, but at the same time mean more complex system, because here we have 3 different signal levels that we need to decode at the receiver side. Also, we have 6 elements. That means we have to have wide bandwidth. Okay, that's why usually when I say high data rate, that comes with the higher bandwidth, and that is the relation between them. Okay, so this is a multi-level 8-bit 60. So this is a summarization table to summarize all the techniques that we have. So in the unipolar, we talked about non-return to 0. We said it is costly. There is no self-synchronization if we have long run of zeros or long run of ones. And we said there is a DC component here. For the polar category, we talked about non-return to 0 level, non-return to 0 inverted. We talked about the biphase. Biphase is for differential and differential Manchester encoding. We call them biphase. So these 3 different techniques, we said the first 2, they have no self-synchronization if there is long zeros or ones, and they do have a DC component, both of them. For biphase, we do have a self-synchronization through what? The mid-bit transition. In the differential in the Manchester and differential Manchester, we have a middle bit of the transition used for synchronization. They do not have a DC component, but we said why they have high bandwidth? Because they have 2 signal elements per bit interval. We talked about AMI and Z2 ternary for the bipolar. We said the AMI has no synchronization for long of zeros, and it does have a DC component, but we said we will fix the synchronization problem using scrambling. Multi-level, we talk about 2 techniques here for higher data rate. The second encoding we done from the line coding. Okay, the line coding is used in every time we encode digital data to digital signal. There are other 2 types. We said we will use them sometime. For example, block coding. So why we need to use the block coding? The block coding is used for error detecting, and it's used to help with the synchronization. So there are 2 advantages when we need to use the block coding for synchronization and error detection. And what is the block coding? The block coding is a very simple technique. It's changing a block of m bits into a block of n bits, where n is larger than n. So if we have 5 bits, we change them to 6 bits. If we have 6 bits, we change them to, using the block coding, to 7 bits. Replacing smaller number of bits with higher number of bits. We don't like that, because that will decrease the data rate for our data. But sometimes we have to do that in order to do synchronization and error detection. So this is what we have. We have an m number of bits. We do a block coding. The block coding will change each number of bits to a larger number of bits. So let's take an example so we understand this more. So let's say we are using 4B, 5B block coding. What we mean 4B, 5B, we have in 4-bit in, 5-bit out. So we are coding to 5-bit. One important thing I want to highlight here, the block coding happened before the line coding. As you can see in the process here, we do the block coding, then we do the line coding. Okay, the line coding, the techniques that I just finished describing, this is called line coding. So this is 2 separate processes. Block coding happened first, then line coding happened first. For example, we are using non-return to 0 inverted here. Then we send the digital data. At the receiver side, what we will do, we'll do the decoding first, then we will do the decoding for the block coding. So there's 2 processes. First, block coding, line coding, then decoding the line coding and decoding the block coding. So 2 separate steps in order to achieve that. So this is an example of 4B, 5B. When we have 4B, that means we have 2 to the power 4 number of bits. So that means how many combinations we have? when we are sending data, we have even 16 combination of data that we need to block code. So this is the block code for the 16 different scenario here. As you can see, we are using 5 bits. That means we are using 2 to the power 5. So how many different combination of 5 bits we have? 32. We have 16 here. We have 32 here. How many we used here? We have used only 16. So the other 16 we can use some of them here, as you can see, for control sequence. For example, for idle, for start delimiter, for end delimiter, for set, reset, idle, quit, different control sequence we are representing using a different block coding. So we were able to provide a control information. Also, the rest of the encoded sequence, the block coding sequence that we did not use, we can use them for self-error detection. So if we receive something not in this table, not here on the block coding, not in this list, that means it is an error, right? So that's how we can use an inherited, it's called inherited error detection. So that is basically block coding. Very simple techniques. Used for what? Used for two things. Synchronization. How we are achieving synchronization using bit coding, using block coding in this scenario. Let me finish this, I'll come to your question. How we are achieving synchronization. As you can see here, using the data sequence, we have 0, 0, 0, 0 here. We have 4 zeros. We are changing that to 1, 1, 1, 1, 0. So basically, using the block coding, you will not see anywhere here the 3 consecutive zeros more than 2 zeros. We have a problem with the, if you remember, with the non-return to 0 invariant. We have a problem with the long run of zeros. When we have a long run of zeros, we lose synchronization. So we can fix that by using the encoding that we listed here, replacing or having the condition that there is no more than 2 zeros, consecutive zeros in the block coding. So if you look here, there's only 2 here. There is only 2 here, between them 1. So you will not find a 3 consecutive zeros. And that's the way we fix synchronization problem. For 1, we do transition of the polarity, right? And that helps with the synchronization. Yes, you have a question?
So is it kind of like assured that, like, it kind of seems like by adding the extra bit,
Yes.
there's like, you're doubling the amount of information.
Excellent observation. Yes, that's what I said. We are adding more bits. That means if I want to send 8 bits using the block codings, the 8 bits end up as what? 10 bits. So that's lead to what? Decreasing the data rate that we have. And that is, you know, one of the disadvantages of block coding. That adding more bits will make the data communication efficiency less in this scenario, but we are compromising that by what? Adding synchronization, adding self-error detection. So that is the advantages of block coding.
So right now in this very example, by adding 1 bit, we're doubling the amount of messages going to be sent, but we're leaving that extra.
We are not doubling. Why you are saying doubling? Let's take this example. If I have 0, 0, 0, 0, 0, 0, 0, 0, 1. I have this data. I want to send this data using, but I want to use the block coding technique. So how this data will be sent? The first 4 zeros will be replaced by 1.
4 ones and zeros.
4 ones and 0. The second 4 bits will be replaced by 0, 1, 0, 1, 0, 0, 1. So actually we have 8 bits originally and we are sending 10 bits. So we're not doubling the amount of the data. We are increasing it by 10%.
Oh no, I didn't mean like doubling the bits. It's just doubling the number of possible messages.
Yes, that's true. Here we have 16 bits, 16 different combination of data we want to send, right? By using the 5 coding, the 4B, 5B, we will having 32 different coding that we can use. We used here only 16, as you can see, for the data that we need to send. We used here 1, 2, 3, 4, 5, 6, 7, 8 for controlling. The remaining, which is 8, we use them for error detection. So actually we have more control over the bits that we have.
It's just like 100% like it kind of seems like it's doubling that it's leaving a space for like saying like these are all errors. So it's like all like on like that column of control sequence after all that control sequence like everything
Yeah, the rest is error. So we use them as error. So if I receive what 1 1 1 1 1, I don't know, out of these combination, if I receive that, I will consider that as error detection technique.
So is the error detection assured, or is there like just like is it just like giving a very big possibility for error?
This is,
error detection?
of course, it's not assured because I can have alternative of the bed. Okay, so this is just a small way of doing error detection. We have a chapters about error detection. We will explain error detection in more detail, so you get a better understanding of what we do. We will calculate something called checksum from the data where we store it. So having the checksum with the error detection, both together they work. Okay, let's continue here. So let's go to the scrambling and what we mean by scrambling. Scrambling is we are going to replace the same number of bits with another number of bits other than the block coding. That is the third category we want to discuss. We discussed line coding, we discussed block coding, and we want to discuss now scrambling. So scrambling, we have 8 bits, we want to send them, we will replace them with another 8 bits. So it's no more data to be added. Another highlight about scrambling, it is done at the same time as the encoding, not a different step as a block coding. So here's an example of scrambling. We have if we want to use, for example, AMI. As we said, AMI has a problem with a long run of zeros, right? So we will fix that by using scrambling. In order to do that, we can do that at the same time we are doing the line encoding. We will do the scrambling at the same process. It's not a different process. So how this is done? This is done as the following. So if we have 1 and another 8 consecutive zeros, we will replace these 8 consecutive zeros using this technique, which is called B8ZS, or we call it bipolar 8-0 substitution. So we will substitute for every time we have 8 consecutive zeros. So here we have 8 consecutive zeros that will be substituted by the 0, 0, 0, V, V, 0, V, B. So that is the code we will use. Sorry, you got the idea. That's the code we will use to substitute the 8 consecutive 0. We use either this code or we use that code, 0, 0, 0, VB, 0, VB. We have 2 different codes. We will use them to substitute the 8 consecutive zeros. And that helps with the, the synchronization. Instead of having 8 consecutive zeros, that will eliminate that to maximum of 3 consecutive zeros. So that is how we fix synchronization problem with the AMI. So the question is, when we will substitute with this code, when we will substitute with this code.
So scrambling has to do with like long sequences of repeating.
Yes, long sequences of, not any long, it has to be 8. So for every 8 consecutive zeros, we will replace them by 0, 0, V, B, 0, V, B. What is V, what is B? V is the same polarity as the non-zero, the previous non-zero pulse. So the previous non-zero pulse is what? Is positive, so B will be positive. B here is an opposite polarity to the previous non-zero pulse, which is here positive, so B will be negative. 0, V, B. So here we have 0, 0, 0, V, B, 0, V. V here is negative. Why? Because previous non-zero pulse is what? Is negative, so it will be V is the same, so that's why V is negative. So we will use the same code, which is 000 VB 0 VB, but the V and B will change their polarity depending on the previous non-zero pulse polarity. And that helps in two things. That helps, of course, in the synchronization. As you can see here, we have if I have 16 zeros, the first 8 zero will be replaced by this code. The other 16 zero will be replaced by the other code. So that is a big advantage of using AMI, scrambling in AMI. And this is done in the same step, as I said. The second technique of scrambling is called high density 3-0 substitution, HDB3, high density bipolar 3 zeros. From the name, we know that we will replace 4 consecutive zeros with the code. 4 consecutive zeros with the code. We have two different codes we use in here. One is the B00V, and the other one is 000V. So B00V, we will use it when? It will be used when the number of non-zero polarity since last substitution is even. Again, the B00V code will be used when the number of non-zero polarity after the last substitution is even. The 000V will be used when the number of the non-zero polarity after the last substitution is odd. So let's take a look here. We have this code 110000, etc. We need to use the HDB3 technique in order to scramble that. So HDB3 technique says every 4 zeros, replace them with one of these codes, right? And that depends on if it's even or odd. So for these 4 zeros, because it's given here, because the number of non-zero pulses here is after the last substitution. We don't know when is the last substitution happened, but it's given here in the slide. It's even. So I am going to use the B00V. B00V. Then here I have another 4 zeros. These 4 zeros will be replaced by the 000V because the number of non-zero pulses after the last substitution, this is the last substitution. How many non-zero pulses we have after the last substitution? We have only one, that is odd, so I am going to use the 000V code. Here, for the next 4 zeros, here, the number of non-zero pulses is even, so we will use the B00V code. So basically we have two codes. We use one of them based on the number of non-zero pulses since the last substitution. And that will help what? That will help with keeping the DC component 0. A lot of information, right? Yeah, today chapter is a little bit condensed that you need to review it after I finish, okay? I'll give you a lot of information, but after we done, try to review it as soon as possible, like tomorrow. If you wait till next week, everything I said, you will forget it. I promise you that. So let's continue here. We have two types of transmission modes. Do you want to take a break or just finish the chapter? Break? Okay, let's take a break for 15 minutes. Okay, we'll continue the class. This is the second part of the class. So in the first part of the class, we saw two different types of encoding. We categorized them into 3 different categories. We said line coding, block coding, and scrambling. For line coding, we discussed different techniques, and we saw that each technique has its own advantages, disadvantages. We saw how we can determine the synchronization problem, how we can determine the DC problem in each one of these techniques, how the mid-bit transition help in the synchronization, and for example, the biphase techniques for the Manchester and differential Manchester. Then we saw how the block coding can help improve the disadvantages of some of the line coding techniques. We saw how we combined the non-return to zero inverted with the block coding, where we are able to get rid of the synchronization of the non-return to zero inverted technique by replacing, 4 bits by 5 bits. But we couldn't solve, for example, the DC component in the non-return to zero inverted using the block coding. We saw how we solved the problem of synchronization with the AMI technique using the scrambling, where we changed 8 consecutive zeros with a different code with different bit patterns, such that we solve the synchronization problem. So for example, when we have a long distance communication, we try to use one of the techniques that we mentioned here that has the lowest bandwidth, or the lower bandwidth. For example, AMI, as we saw, it uses only one signal element. That means it has lower bandwidth, right? So we can use it for long distance communication, but we cannot use it without scrambling. Long distance communication without scrambling will make no sense to use AMI. So we add the scrambling for AMI. Now we can use it for long distance communication. Next part of the class here, we want to talk about different transmission modes. Data transmission can happen in 2 different ways, either parallel or serial. We can send data parallel. That means we send the bits at the same time. Like if we want to send 4 bits, we will send them at the same time. That's called parallel. Serial, we send them 1 bit at a time. Serial transmission can categorize into 3 different types: asynchronous, synchronous, and asynchronous. We will be focusing in this talk on the first 2 parts, synchronous and asynchronous transmission. And that's the one that we use for data communication. So here, the parallel transmission, as you can see here, the sender wants to send these different 8 bits. So using parallel transmission means we have a data link. We have a link for every single bit we want to send. So we have 8 links. We will send these 8 bits at the same time using these 8 different links. You will find parallel transmission for example, if you open your desktop. If you open your desktop, I mean your computers at home, some of the cables, they are really wide, okay, especially the one comes from the hard disk connected to the motherboard, they are that thick. So parallel transmission work fine when we have a short distance. But when we have a long distance, we cannot provide a separate link for each bit we want to transmit. So data communications doesn't happen using parallel transmission, happen using serial transmission. So serial transmission, on the other hand, is what? Is sending the bits one at a time following each other. So that is a serial transmission. We have only one data link and we use all the bits. We emit or send the bits one at a time. That's what we mean by serial transmission. Now, for serial transmission, we have 3 types. The first one is asynchronous transmission. When I say asynchronous transmission, what I mean? I mean the time is irrelevant. The time is not important for asynchronous transmission. There is no need to synchronize the clock between sender and receiver. That's why it's called asynchronous. We don't need to synchronize. So if we don't need to synchronize the time, I mean we don't need to synchronize a time between sender and receiver, we have to synchronize the data in a different way. So what we do, we will add a guard between the bytes of the data that we are sending. As you can see here, we will add a bit that will tell us when that byte start, when that byte of data end. So for these 8 bits, or for this 1 byte, we will have 0. 0 means that's the first that's the beginning of the 8 bits. 1 means that's the end of the 8 bit, and so on. So we will send the data byte at a time. So that is the asynchronous transmission, 1 byte at a time.
It's always 8. It's like totally 10 bits.
It's
Eight as data
for
and-
asynchronous transmission, yes, we will use 1 byte at a time, so that means 8 bits at a time. We will add 1 or more bits as a guard between to identify the starting of the bit and the ending of the 8 bits. We will have different types of gaps, so the gaps can be, we will fill them with idle data, so the end of the bit can be 1 bit, can more than 1 bit, depending on how much is the gap.
So how does the receiver understand that this is, if you have more than 1 bit, how does it understand?
That
this
is a good
when it
question.
starts?
So how the receiver will know that this 0 is actually the beginning of the bit, is not the actual data in the 8 bits? That's a good question. That's why we don't need to synchronize the time here. We only need to synchronize 1 byte at a time. So when we started transmitting, there will be an agreement between the sender and the receiver. What are the combination of the zeros and ones, 1 bit or more than 1 bit, for letting us know when the 8 bits start. Then the receiver job is to count after that. That's to answer your question, how many bits we receive. After we receiving 8 bits, the receiver will know the next thing is coming is the end of the bit. So we'll expect the end of the bit pattern, then we'll expect after that the beginning of the bit pattern, then after that we'll count 8 bits and so on. So that is asynchronous transmission. Asynchronous transmission, we don't use it in transmission. Why? Because it has low data rate. So for local area network, for wide area network, we use only synchronous transmission. So why we use asynchronous transmission? It is used in a specific application. For example, the keyboard that I have here, when I press on the keyboard, I am really sending only 8 bits, 1 byte, right? So that kind of asynchronous transmission can be used between the keyboard and the computer for a limited low data rate applications. So for high data applications, what we use, which is what we have in the internet, we use synchronous transmission. So the synchronous transmission, as you can see here, it's called synchronous because the time is important between the sender and the receiver. The synchronization of the clock is very important to synchronize the beginning of the bits. So there is no extra bit we will add with the synchronous transmission to tell us when is the byte start, when is the byte ends. And also the data will be sent as a stream. We don't send the data as 1 bit at a time. We send them as with a frame. The frame has 100 bytes or 1,000 bytes each frame. So we don't use a transmission, a guard or a extra bits to determine the beginning and the ending of the byte. What we use the clock. So the timing, the synchronization between the clock, between the sender and receiver need to be synchronized, so the receiver will be able to receive the same number of bits. As you remember, we said when the timer of the receiver is like 1% faster than the timer of the sender, we end up receiving hundreds or thousands of bits when we have 1 kilobit per second data rate. When we have 1 megabit per second data rate, we receive 1,000 or 1 million. 1,000, whatever. We received extra bits, right? So that is because the timer of the receiver is faster than the timer of the sender. Using, of course, the different encoding techniques that we learned, using the mid-bit transition, using the polarity transition, these things help the receiver keep the clock synchronized with the sender. So there are many things the receiver uses. But what I need you to know, there is 2 types of transmission. That's what you need to get from this slide. There is a synchronous transmission, synchronous transmission. What we use in the on data communications, we use synchronous transmission because the synchronous transmission gives us the data rate that we really need to communicate using local area network, wide area network. Asynchronous is used only for small applications because it has very low data rate. So that is a different type of transmission mode. As the third one here, which I don't have a slide for it, let's go back, which is the isochronous here. This is isochronous. If asynchronous doesn't, then the time is not important, and synchronous, the time is important. So what is isochronous then? Isochronous is used for special application. For example, for TV. Okay, when you send the TV image, as you know, image sent per frame. So if we are sending a TV image using different frame rate, we don't only care about the synchronization of the time. We care also about keeping the same data rate for the whole communication length. So synchronous here, the time is important, okay? For isochronous, not only the time is important, add to that the data rate, keeping the same data rate from the beginning of the transmission to the end of the transmission. If the sender is sent with an X data rate, there is all the frames that we send should be received by receiver by the same data rate. If we increase the data rate, and this is usually used with the TV communication when we send TV images, that will have a different experience at the receiver. So the receiver does not want to receive the images at different, speed, right? That will, okay, we will still receive them, but the image will be disturbed. So that is isochronous. Isochronous is time and keeping the data rate fixed for all the duration of the transmission. Synchronous only synchronizing the time. Asynchronous doesn't care about any one of these. Only send me the bytes. I don't care about the data rate. I don't care about the fast of the communication. How fast is the communication? As I said, most of the data communications happens in a serial communication that we have now. Parallel is used in specific applications. It's short, very short distance. All right, so that's it for chapter 4.